majority of AI workloads still run on x86 and NVIDIA GPUs, architectures that only make up a fraction of what's out there. So the question is, how can we make AI run everywhere, and what role can GCC play in that? So this session isn't a talk, it's a discussion. We're here to explore the intersection of GCC and AI. So where GCC already shines, where it struggles, and how it might evolve to meet the AI workloads. This is a discussion on GCC for AI and not AI for GCC. So a little bit about me. I'm Pietra. I work at Embecosm as part of the GNU team and AI tooling team. I worked on development of the open hardware group GCC compiler toolchain. And with the background, I was part of one of the first groups to get PyTorch to run on a bare metal microcontroller. So if you look at this diagram, you can see where I live. I deal with taking PyTorch models, compiling it into optimized PT files, and then having the GCC compiled runtime, manage all the execution. And my daily challenge is the full pipeline. So from the delegate partitioner all the way to the custom kernels, which are from the dedicated accelerator. So yeah, I live at the edge of where traditional compilers meet emerging AI workloads, dealing with mixed computing resources. These are some of the topics that I want to cover today broadly. Challenges, opportunities, roles of GCC, and where we can extend it. We also have Jeremy, which I guess most people know. Don't know if you want to. We may have seen.
So just in case, I run Embecosm, and to put this in context, we're using GCC on pretty much all the AI work we do, but I'm regularly rung up by potential customers saying, Jeremy, does your company know MLIR? And somehow LLVM's managed to get the brand, because that question usually needs to be translated in, I designed an AI chip and didn't realize I needed to think about the software. And MLIR and AI software have become synonymous. And there's no reason why GCC shouldn't be. So what's GCC's equivalent of, I need to know about X, which is GCC's answer for AI implementation. But this is Pietra's leading this BoF. I'm going to be the runaround with the microphone.
So the first question is, so GCC already has powerful auto-vectorization and parallelization. How do we extend that to AI-specific kernels like convolutions, matrix multipliers, and attention mechanisms? I don't know if anyone has any thoughts. Yeah?
I was thinking, so as of recently, we have this machinery in GCC to understand the code for CRC computations, cyclic reduction. You know what I mean. If that would be a fit to figure out some of the algorithms or code that people use and map that to corresponding hardware instructions, one idea.
So can you? Okay, it's just a recording. So I think the answer to MLIR, as I understand MLIR, it's probably a very, very simple-minded opinion on MLIR. So if you go back to the 2017 GCC, it was still a summit, I think. I presented on the middle-end array expressions, which I think is basically what MLIR is. But the reception wasn't all over positive at that point. There were two AI, it was before the AI thing took off. And so that would be my answer to MLIR. Knowing nothing about what actually MLIR is in LLVM. But I guess it's that thing. So there's a paper. At that time, we still wrote papers. It's also on, there's a wiki page, and it's attached there, so you can review it and make yourself an opinion if that's nice or not nice. So there are patches on the mailing list implementing that, which of course they don't apply anymore. But yeah, can you maybe try in a few words explain what MLIR is?
Like, yeah, Jeremy, do that.
So in LLVM, you've got IR, which is their equivalent of RTL. Okay, and the idea is that despite a lot of effort, LLVM IR sort of believes it's in a C, C++ world. And the idea of MLIR, which is multi-level IR, the ML is not machine learning, it's multi-level IR, it's about 7 years old, is to try and abstract higher up and say that the operations you do in IR, many of them are completely abstract and independent of actually that it's C and C++. And the idea is it generalizes the idea of an intermediate representation that you then specialize. So the Fortran front end has a Fortran flavor, a dialect of MLIR. And for AI, the entry point, at least if you're coming from TensorFlow, is something called HLO MLIR, and I can't remember what the HLO stands for. So all MLIR is a generalization of the concept of an intermediate representation, trying to get away from being C, C++ centric, and I suspect someone's got their hand up because they can clarify that a bit more.
Sorry, I'm in the conversation with MLIR. I actually had another point. That's not MLIR. Since you mentioned PyTorch, I can say I had to deal a lot with it recently and try to build and optimize with GCC. And leaving aside, the loop optimizations and all these, vectorization and stuff, it's actually a very, very big project that, from what I understand, does all kinds of stuff. So like a toolbox that does training, inference. You can run on CPUs, GPUs, CPU only. You can run across data centers or something like that. So there's lots of components, lots of ways of running it. And it is an enormous kind of package that has multiple libraries that do a lot of this optimized stuff. So I think it's obvious a lot of people use it. I think all the important AI players do use it in one capacities. So, one easy step we could take is to treat something like PyTorch as a, target workload. So currently when we talk about optimizations, right, we talk about spec and bench, the embedded benchmarks and all that, and say, if your optimization does well at those, then that's a good thing. But maybe we should, build up a bit more expertise in the community on things like PyTorch and the kind of challenges that presents, so that we can evaluate optimizations on those. From my kind of very initial experience of just a few months, I can tell that there are lots of intrinsics code written in SIMD intrinsics, and you care about the compiler not messing those up. There is a lot of LTO optimizations, lots of cross-module stuff that maybe the linker and the dynamic loader should be doing some stuff. There are lots of optimized math libraries and communication libraries that maybe it's not GCC's job to fix, but somebody else's is. Yeah, and there's a lot of play with different data types. So there's quite a lot of stuff that's not spec shaped, but a compiler could probably improve.
So I think just carrying on from there, today's strengths with GCC, we can look at IPA optimizations and drive that further with large AI workloads. That's a good step we could take today. Coming back to the point about MLIR, LLVM IR, there is a debate about the shape of LLVM IR in the community at the moment. A lot of the loop optimizers are more suitable to be done at the MLIR level. It is not necessarily that LLVM IR is C, C++ shaped. It is just that they are looking to simplify it in some of those spaces, and there is quite a big discussion that is going on Discord at the moment about the future of LLVM IR. Coming back to MLIR, you're right that it is multi-level IR, but what it's giving people is a framework and the same set of interfaces to operate on an intermediate representation. So that means that if people are moving between different dialects, they don't have to learn new interfaces, And the debugging techniques and the tooling that they can build is pretty common when they go from, I don't know, a special dialect someone invented for Fortran to an OpenMP dialect to an SVE dialect to an AVX512 dialect. They've invented dialects for all sorts of things. So you can view MLIR as a meta level IR for creating more IRs. That's the picture I have in my mind about MLIR as the project. So does GCC need that kind of abstraction? I don't know. But it is worth thinking about it from the point of view of software engineering principles and those aspects of MLIR. The second part of what's coming for free in MLIR is a whole bunch of dialects that deal with linear algebra. So there is a polyhedral dialect, there is a lineage dialect, and there's a higher level abstraction of loops that makes it easier to do things like polyhedral optimizations. And those are really applicable for the ML kind of workloads because you don't need to deal with the exception cases that you have in C, C++. You don't have to worry too much about aliasing. That takes out a whole bunch of things. So these are regular shaped loops that are more suitable for the kind of analysis that polyhedral was built for. At least this is how I understand the MLIR landscape.
Yeah, so to comment back on that, so basically what I was referring to, the GCC work I was referring to, is basically doing the machine learning thing of representing loops as a single statement, for example, and not a multi-level IR that we'd have generic is our multi-level IR. Like we have a generic dialect for C++, we have one for C, we have one for, well, not for Fortran, it has its own IR. So we do have front ends which have their own IR that are not being operated on with the tree interface. That would be one of the MLIRs we have is trees. And we've basically decided that we rather want to extend Gimple when necessary than fragment it. Like we are not extending RTL into different dialects, but so we are not fragmenting it, but we are trying to cover all front-end semantics in Gimple. And I think Gimple is quite more high level than LLVM IL. So I'm not sure whether we need a language-specific or domain-specific Gimple, and I don't see the use or how it could be maintained. I mean, but I think that the point is possibly not. So you're basically feeding along a lot of black boxes, right? And yeah, and we do have, like, we have a lot of internal functions that are kind of magic to most parsers, and we shovel them through. So we are like the assume thing and stuff like that. And I think have found a pretty good balance of how to extend Gimple. So there are, of course, some design decisions that make some kind of extensions difficult, like having multi-output statements is going to be a pain in the ass if you're not going the assembler statement route. But otherwise, other than that, we are quite flexible there.
Hi, so I actually run some ML workloads in production, and I have a little bit of controversial take here, which is we don't need GCC to do kernel level optimizations. Here is why. So the backbone models, like large embedding models and large transformers, need GPUs. They can't run on CPU effectively at all. And for that, we already have specialized libraries that can take PyTorch models and they can run on GPU, very, very effectively. But where we have struggles right now is with, head level of this ML architecture. So for example, it's common to use all these embeddings as an input to a large tree ML model, like XGBoost or CatBoost. And here we have a lot of struggles, and maybe those models is where GCC optimization can actually be very helpful. So right now in our production, we have hundreds of CPU cores running right now, just computing these tree models. And they work on Intel, they crash on AMD. So maybe if those three models were a benchmark on which GCC is improved, that would be much more useful for ML practitioners than trying to optimize actual neural networks. And in fact, those final levels are often doing just dot products, like crazy many dot products. So maybe we should have some benchmarks, and we should optimize GCC specifically on those final levels of ML architectures, and maybe not even try to optimize large embeddings, large transformers, because that's where the problems are mostly solved.
I also want to highlight what I think the GC and OVM kind of play a bit different games here. Like one of the reasons why MLIR is the thing and people discuss it, and why they talk about these dialects and all these various tensor abstractions, is because they don't, in that game, they don't care about the Clang pipeline as such, right? It's not Clang consumes C++ code, then it goes through these abstractions and then it spits optimized stuff, right? It's other high-level code generators like JAX, XLA, or whatever they call them. They do this big, they have this ML program that's broken down in graphs in their own high-level, logic, and then they generate these MLIR, potentially dialects, and then they transform those in these domain-specific logics, the merge operators or whatever, and then eventually they'd like to, for the parts that end up running on the CPU, they end up, they like to lower it to LVMIR and just get the free code gen from LIR, and then some other part of the system ends up offloading stuff to the accelerator or through libraries. Whereas GC is, well, historically is primarily a ahead of time system compiler for Linux. That's its bread and butter. You take C, C++, Fortran code, optimize it well, generates good assembly and runs it. We also have like the offloading stuff, of course, but it's still the same paradigm. So unless GC is willing to kind of consume, to be plugged into these frameworks that do all these non-C things, then I don't see how an MLIR discussion could fit into GC.
Yeah, I think the first question is what would produce the input to GCC, and if it's PyTorch or whatever, would it use some kind of a dialect of C or libgcc JIT or whatever else, be a new front end for GCC that's also doable, and then what it should emit, if it should emit code for normal architectures or for the offloading architectures, and how it what libraries it would use, and so on. But inside of GCC we can use the internal functions a lot and other stuff, and it could be doable.
What research into optimizations for AI? Let's get you on. Okay. Oh, fine. So, can you tell us what people who are doing research into AI optimizations, what are they using? Are they just using MLIR, or are they doing something else?
Probably easiest for me to pick that one. So, I think you picked up the area, which is MLIR is mostly used for people doing graph transformation. So if you look at OpenXLA, which is the current flavor of the month for doing graph transformation, it's basically doing linear algebra on graphs. and combining nodes and so forth. I think just to put that in context, people get a bit hung up because we're compiler communities about compiling your neural network down to binary. In reality, almost all neural networks are interpreted in the sense that you work at runtime, you walk over that graph saying, this node says do a convolution, this one says do a multiplication, and you pull in the arguments to do it. And the reason for that is, first of all, the interpretive overhead is not big because the cost of the computation in the node, and of course that is compiled, is huge compared to the cost of actually walking over a graph. But the second reason is that large language models modify their neural networks. And so there isn't a fixed neural network you can compile because the large language model may change that neural network. So you have to use this interpretive mode when you're evaluating large language models. And so that sort of affects. And so perhaps part of the question is, if we're living in a world which is inherently, the focus is, I think someone said, is GCC and the kernel. I think the MLI, the whole abstraction stuff is perhaps not so important, but it's still research stuff. So anyway, Romana had his hand up.
I believe the space for ML compilation to the variety of compute is actually quite huge. In some cases, it is quite true that you have an interpretive mode. If you look at NN API in Android and others, there they go through an interpretive mode. But even there, what they're looking to do is find parts of the graph and actually compile them ahead of time and cache them. Because the NN API in Android has a direct connection to, if your phone is spending a lot of time compiling your ML models all the time, you're going to see an effect on your battery life. That's one part of it. The second part of it is there are a number of people who are building microcontrollers which are powered by coin cells with ML accelerators. There is quite a model like what Pietra showed here of ahead of time compilation and calling out custom kernels or custom libraries. That is one area that people are working on. And the third one, which is sort of dominated by today's world of large data centers, large language models and others, that is a world where there is a combination of interpretive execution, there is eager execution, and within PyTorch, there is a plethora of maybe 4 or 5 compilers in there. And they've evolved it over the last 5 or 6 years. Okay, so that is one part which is changing. Coming back to Jakub's point about finding the interface between an ML framework and GCC, I think that's a really tough problem because that takes a lot, that doesn't stabilize, and they like to keep changing things all the time. It's not dissimilar to how Rust is operating or has operated in the past. I say that from experience of trying to build an ML compiler with a layer with Apache TVM and trying to build it for 3 front ends, TensorFlow Lite, PyTorch, and ONNX. And the biggest challenge we had was actually keeping up with how the operators changed, and the operators were not mathematically specified. So you had all sorts of fun and games playing with that because it was down to the interpretation of the framework about what the semantics of each of those operators were. Yeah, that's how it is. And lastly, for Nick's question about what are people using for research today, most people seem to be, it's moved from build my own compiler with Python to now a dialect of MLIR, which transforms from one input dialect into another input dialect to prove the point that the research is making. That is what MLIR is being used for. So a lot of the research community for ML compilers seems to be shifting into that direction. That seems to be what is happening, and that's what they're using.
So I think Romana makes an important point we need to keep bear in mind is this is still a bit of a wild west out there and there is no consistency. And I'll give you one example which bites us in the backside every time, which is when you want to work on images, you have a tensor with essentially 3 dimensions, your X point, your Y point, and whether you're red, green or blue, your channel. And PyTorch and TensorFlow cannot agree whether you do it as XY channel or channel XY, which means if you take a model from TensorFlow and try and run it in a PyTorch world, you do a massive transpose of your input matrix and you halve your performance. And that's the world we live in. But Romano is absolutely spot on. I think Richie made a point when we were talking earlier that actually the problem you've got is people are still fighting to be dominant and number one. I went to Euro LLVM, I heard 3 brilliant talks on compiling PyTorch using the LLVM infrastructure from, I think, Google, NVIDIA, and AMD. All 3 different, all saying their problems, and none of them talking to each other. so, you know, we're still at that stage, which means, you know, plenty of time for us. Has someone else had their hand up? Okay, Pietro, do you want to go?
Yeah. So the next question is, so we've seen a flood of AI accelerators. We have tensor cores, NPUs. Supporting them usually means that we need new GCC backends, but is that scalable?
Richie.
So I think the point was already made that maybe we shouldn't try to optimize the actual dot product kernels or whatever, because as far as I understand, it's not the dot product you're optimizing, but you're optimizing to your memory hierarchy you have, because you're obviously memory bound, right? And it's not about doing the multiply faster. It's about getting your data to the multiplier. And compilers are notoriously bad in guessing what your memory hierarchy is. So these kind of optimizations is for ChatGPT to do, right?
Again, I'll draw to the variety of hardware. In some cases, like the coin cell accelerators or the small ones, memory plays a really important part. It's important to make sure that you're fitting in the memory budget. So putting in memory allocators becomes a really big problem. And I know of people who've tried to use SAT solvers for that. To do a prototype, to prove that the hardware will work, they've thrown a SAT solver at it to make sure that they can do an allocation properly. And they've done things with affine expressions to figure out what the loop structure looks like and how they should deal with the memory areas. So a lot of the concepts that we have in GCC with respect to live ranges or traditional compilers still apply there, but because of the variety of compute, it's quite difficult. I also fear that the abstractions we have are simply just not suitable for some of the kinds of neural accelerators that are there. So I don't see us playing a part in that particular area that easily, especially with the accelerator part. With the extensions in the CPUs or maybe in the GPUs, maybe there is a part to be played. I don't know enough about that to judge. But again, the problem is because we are so shaped with C, C++, and Fortran, I don't know how our past pipeline will react to those kinds of extensions like the matrix extensions and others. So that would be something to think about.
Someone can correct me if I'm wrong, but do I remember right that the latest C++ standard discussions, there are talks about standardizing like BLAS operations or something like that? Because if there are, then maybe that could be a vehicle to, maybe get GCC to treat them, less like library codes. It just needs to shepherd through to libc C++ or whatever, and or OpenBLAS or whatever, and maybe as first-class matrix operations that maybe could then, evolve as IR to handle them in more high-level, and then maybe even use some of these extensions that some backends have. We have some targets that introduced matrix state and operations that currently are just used by intrinsics, but hypothetically a compiler could do this. In LLVM, the MLIR, I think at least half of the MLIR dialects are there to add, these tensor abstractions to the dialects and compile for those. Maybe that's a direction we could be taking.
So that's exactly what these middle-end array expressions did. Yeah. Basically, the original idea was in Fortran you have these expressions on arrays, right? Where you can write loop nests as a single statement, and those carry on through Gimple. They're basically SSA. You can work like on those.
And that's also exactly what these CRC internal functions are basically. So just with the difference that here the compiler figures out from the C, C++, whatever source code, and you don't have a direct correspondence in the source language, but then you have them in some IFN again, like expression, and the individual backends either lower them to their hardware instructions or some whatever library code. So yeah, that's I agree. That's very feasible.
I just want to just generalize that, just to put a bit of context on here. The one thing that's not mentioned here is quantization. Can I check, do people know what quantization is? No. Okay, so the idea of quantization is that when you train a model, you want your weights, whether your neural network files or not, to be quite highly resolved, so 32-bit integer. And any biases you have to be 32-bit. That's a general shift on the node. That takes up a lot of space. And when you come to actually inferring the model, you don't want to be shipping vast tensors full of 32-bit values around. So can you actually say, but I can simplify it down to something small? And that's called quantization, where you reduce your 32-bit values to just 8-bit values. And it turns out that actually that is not just a, hey, we'll just round it to 8 bits because then it doesn't work. It's actually very hard to get that right. But people are starting to understand. And what you find is, in the example that Pietra didn't have in the detail there that she's worked on, actually has the ability to quantize down anything from 8 down to right down to 2 bits. And it can quantize the activations and it quantize the weights. Now you start doing a bit of combinatorics and they say, well, executorch, which is the embedded version of PyTorch that was running there, has I think 142 operators. 142 operators. And then I need a variant implementation for all the 8-bit, for 8, 7, 6, 5, 4, 3 and 2-bit activations, 8, 7, 6, 5, 4, 3, 2 weights, and all combinations thereof. And suddenly you realize, actually, yeah, I've got an awful lot of kernel variants I need to compile for. And that's just for executorch. PyTorch has nearly 4,000 operators, and anyone can add more operators. So I think just saying, hey, the kernels are, okay, NVIDIA can write that many kernels, but your small startup with their new chip possibly can't. And I think there is a role for the compiler there that we might want to think about. Actually, no, there is a problem around just the kernels before you even think about, and I agree with, there is a whole lot of linear algebra and how you combine networks and so forth there. So just throw that one into the mix. Pietra, do you want to move on to your...
Yeah. So this one is a use case that I got from the GCC mailing list. I asked if there was anything that anyone wanted me to talk about. And Benoit from Colray got back to me. And they basically pointed out that organizations using GCC, unlike those using LVM, have to rely on the emit-C dialect to bridge MLIR in GCC. So to make GCC a stronger target for the MLIR ecosystem, what are the best paths forward? He suggested 2 approaches that I put there. Should we work on a Gimple MLIR dialect? Or should we leverage GCC's backend, perhaps by defining a machine-dependent MLIR dialect based on RTL for the specialized assembly?
I randomly found this a number of months ago, so there's a very early stages project on GitHub with the name MLIR GCC JIT. Again, described as an MLIR dialect for libgcc JIT. So I have not looked in any detail what they're doing. But apparently they are some, I quickly would understand this as some kind of MLIR front end using GCC code generator via libgcc JIT interfaces. Not sure if that is useful in any way or what state that is actually in.
It would also be my suggestion to, if you want to prototype, try to use the libgcc JIT to directly emit Gimple.
Yeah, I was going to say, I mean, we have the GIMP and RTL front ends, but we currently only use them for debugging. I don't think we intend to make them kind of, interfaces for people programming in GC. Or maybe we do. I don't know. Maybe that's a question to ask. But if there was such a GIMP dialect in MLIR or RTL, then it could be plugged into the rest of the MLIR ecosystem, where someone would need to define how you, lower the lineage, for example, dialect to GIMP, and then from then, if there was a way for GC to consume that GIMP MLIR, then I think that probably is the least friction. The way of least friction to get it into GC compilation pipeline.
There's a certain amount of cyclic thing. I remember Dragon Egg, which was where we had a GCC front end to the LLVM back end, and we're now looking at a GCC back end to an LLVM front end, which is history circulating.
I think we already kind of discussed this, but frameworks like PyTorch and TensorFlow already have graph optimizers. Should GCC aim to plug in as a backend from something like MLIR or build its own front end for high-level models? Don't know if there's anything to add on that. Yep. The next one is AI hardware and algorithms evolve incredibly fast. GCC as a project moves carefully and deliberately. How do we balance the stability with the need to innovate quickly?
I think we should admit that we are not the correct target for the fast-moving forks. So I see no benefit to GCC to try being the hipster AI compiler infrastructure. It's, yeah.
I agree with for GCC as a project, but we still could encourage people to do research on GCC again if they want in these areas, if that makes sense. But of course, that needs some framework and infrastructure as well, which we currently don't have.
I guess we could try to make, for instance, internal functions plugin controllable, and then you would just play with a plugin to add new internal functions and do something with them.
I'm not sure about plugins. I do like libgc JIT more. Maybe we well, you're good at marketing, so maybe we just need the Python interface to libgc JIT that you can write your MLIR translator in Python and not have to use libgc JIT. So great. So I don't believe internal functions are the solution to everything. I mean, they are kind of black boxes, but yes.
I think another answer to that question is having regular updates from people like yourself telling us about what's going on and what's needed. And that way we can actually keep our heads in the game.
So coming back to the point in the beginning, maybe if we're conservative, if we take the conservative approach and say, okay, maybe compiling graphs and doing all this is not, it's in contrast with GC strategy of being a stable compiler. Maybe the way to do it is kind of research all the, let's say, the leaf nodes of all these frameworks. Like, at what point do all of these intersect where GC is now? So at what point do they end up calling glibc? At what point do they end up generating C++ code that must be compile linked? And is GC doing a good job there? So maybe that's a place to do it. And I think, as I begin, I think if we do that, we'll find that a lot of those important places where all of this, behemoth ends up touching the ground, so to speak, you will find it's not spec or not the stuff we traditionally focus on. And I think that's where we can probably make a meaningful improvement. So, I mean, last year, my team and I, we talked a bit about, let's say, locality optimization, where we said, there are performance gains to be had by thinking a bit more how you can group stuff better together. And and that's part of the and that is from AI workloads. We found that. So we found we have like these very peculiar, large, dynamic applications. We find that different effects matter rather than just loop optimizations or vectorization. So yeah, I think maybe that's the way to get better at this without necessarily try to play the MLIR game.
So a short comment. So compared to LLVM, we have the better LTO infrastructure. We are scalable; they are not. So that's something to leverage.
Yeah, I'd agree. Play to our strengths. The other point that I'd make about the Python bindings, I think the Python bindings are a good idea because even in MLIR, people are building Python bindings to MLIR. Now, if you give the bindings and if you give the abstraction to GCC via libgcc JIT and there is a Python binding for MLIR, maybe someone can do some clever stuff on top, which we don't need to see about. So that may be an area to pursue or think about, but we'll probably need some pull before we do it.
By the way, are there any volunteers who'd like to take over maintenance of libgcc JIT?
So you've moved on to lib diagnostics, right?
Yeah, and the static analyzer and things. I'm not really into. I came into this by wanting to make Python better, and I'm now wanting to make GCC better. So my interest in optimizing like Python and all of that's how I got it, was written it for. But yeah, so and to my horror, I'm reading this MLIR thing going, oh, there's a whole bunch of stuff I just don't understand in this that's using my code, and I probably should find out more about this. Yeah, no, I'm serious though. If anyone wants to volunteer as a new maintainer for libgcc JIT, that would be wonderful.
So we also kind of covered this already, but to what extent should GCC evolve for AI? It doesn't need to be a full stack AI compiler, but it could, act as a backend, or if you should add dedicated front ends to AI. Don't know if there's anything to add on that.
I think we probably covered. Oh, no.
Are you, as in Embacosm, being asked to create AI front ends for GCC?
No, as I say, mostly it is, MLIR, which degenerates into, I've built hardware and I realize the software doesn't run, and it mostly rapidly degenerates. Let's just get the thing working before you worry about state-of-the-art compilation. And so most of it is the sort of thing that Pietra's doing, which is just getting this stuff running on actual hardware. And I think in reality, that's where, if you're not Meta or OpenAI or Google, that's where everyone else is, of just getting something working. I think that seems to be what the market's like. So no one's asked. Yeah, I'm curious as front ends, but no one's actually asking for GCC front ends.
Okay. Next one as well. We kind of talked about it. So yeah, where should external tooling take the lead? Like graph level transformations, I think maybe they're better handled outside of GCC, but I don't know if anyone has any thoughts on that.
Okay, just another question. Have you made any contributions to GCC based on your work? Right. I'm getting the feeling that that's probably going to be true across the board, in that most of the development work is going to be done outside of the GCC sphere, and that what we need to do is pay attention to what's going on and tool where we can, but not try to be the leaders, not yet.
I would agree with that, because I think we're still at the stage of people don't know what the question is before we can try and answer it. And I think the stuff that Pietra's doing, I think if we do that for more and more chips, we'll start to say each time we hit the same problem of so many quantizations and for so many operators, actually, how do we handle quantization? How do we handle down at the level of bit level quantization rather than byte or half byte? That might turn into a problem where we need to think about. This problem comes up again and again. Some of the stuff that we sort of glossed over a bit, which is a big thing, which is the memory handling. Because if you look, I think that if we separate out the big machine training, the big GPU stuff from the smaller edge AI, and you'll see edge AI keeps on coming up, and it means different things to different people. But if you're doing low resolution image and audio recognition, you don't need a honking great supercomputer. You can do it on a microcontroller. And I think people are still working through how those work. What is common to almost every chip I see, two things is, one is in-memory compute, because the cost is getting stuff in and out of memory, not doing the compute. And the second is closely coupled memory. So all of these chips have, if you think of the ARC architecture with its CCMs, every single edge AI chip I see that isn't designed to be running a full MMU has kilobytes, hundreds of kilobytes of fast RAM, and all your algorithms around I've got a little accelerator that can do convolution on 3x3 or 4x4. And I have a little microtile goes all the way over my big image, tile at a time. And I've got a DMA that I can use to fill my fast memory. So it's fill my fast memory, kick off thing, get the next bit of memory while it's computing, I've got the result. And it's actually incredibly well defined. And it's not like you're running, you're running in a timed environment where I know exactly how many cycles that. And actually how we represent that and compile for it efficiently, which we know how to do in compilers, so that rather than having to do as we do at the moment, which is make that explicit, we can actually abstract from some of these things, possibly with pragmas, a bit like we do with OpenACC and so forth. I think that's an area where we may end up evolving, just because that's such a common architectural feature. But we'll wait and see. You make the valid point. We're still experimenting.
Okay. And the last one, I think Nick talked about it. How do we best collaborate across communities, GCC, AI frameworks, and yeah, if there's anything that we should be doing to better collaborate.
How does the AI community communicate with itself?
Yeah.
So PyTorch, with PyTorch, TensorFlow less so. TensorFlow tends to be rather internal to Google, and even OpenXLA is dominated by about, I think, 4 out of 5 commits on OpenXLA are done by bots, AI bots inside Google. And AI bots, I'm sure, can write great code, but they sure as hell can't write commit messages. But PyTorch has a mailing list. It is a community. I know it's dominated by Meta. It has a conference. It's in San Francisco in the second half of October. So there is bits of community, but I think it is still the case that not a lot of talking to people. Romana probably knows better than me, actually.
Just offering my perspective, observing it. There's a bunch of places where they meet. A lot of the ACM conferences usually have people talking about AI-related activities. There's usually a compilation track there. There's a compilation track, or there is a little bit of track in terms of quantization and some of those areas to reduce the sizes of models in NeurIPS and other conferences. Almost all LLVM conferences have an MLIR summit ahead of them or after them. So there's a huge hallway track there. Then ISCA and other architecture conferences have an ML track, and they've had that since, 2016, 2017. So there's a huge amount of places where these conversations are happening. It's just that we, in the GCC community, we don't really see a lot of those communications, or we're not plugged into those kinds of networks.
Just out of interest, is anyone else going to PyTorch conference? Okay, so I think Romana's point is made. And I think it is valid. There are all sorts of conferences in other fields that have a track. A huge amount of AI at the LLVM meeting. There's a huge amount at the RISC-V meeting, for example. I imagine that ARM TechCon has a similar amount going on there. So there are places, I think, where we're not yet in the way that LLVM, GCC have tight communities which are really talking very closely on a day-to-day basis. Those really are taking a time to emerge, and that's why we see these silo developments. But this is a first step, this session, and we would have had Nathan should have been talking in this slot about the work 10 story, and we're working with Nathan as well. But so we were going to have 2 AI slots here, but let's keep on having more talking.
So I'm done, but I wanted to ask if anyone wants to bring anything up or anything that we didn't discuss that should be discussed.
Yeah, back, yeah.
As a fun project, we tried to do using ML models to optimize compilers. So we started using a supervised learning, and then started training graphs, and then see we have a model to predict the colors given an LLVM interference graph. So your thoughts on using models to optimize in GCC?
So if someone can remind me, there is such a project inside LLVM, I can't remember what it's called now, and it has been initially promoted by Google, which is to say, can you use machine learning to do register allocation, instruction selection, and instruction scheduling using AI? Sorry? MLGo, that's it. Sorry, I couldn't remember what it was called, and that's been around for a few years. Is it? And we'll get it on the table.
I think the project you're referring to is something called MLGo, and it was used in a way to try and get a predictor for the best set of heuristics to use for inlining and other aspects for a given code base. So that was the interesting thing there. And I don't remember if that was used for register allocator heuristics and others. It could be because you've got a finite code base that you want to really get the best performance out of, and that's where probably an ML model could help you, because you've trained the model to contain all the important information from the source base. So yeah.
So the question was about what stuff we didn't talk about in length. And of course, we can talk about anything. And possibly my concern is not related to this talk in particular, but it's more about the hardware support of things for GCC and bNutils. Like right now, I'm involved in 2 projects. One is, we can call it a standard accelerator, which has RISC-V and some extension. And the other is in-memory compute. And so the question is, possibly at the lowest level of things is, for example, for in-memory compute, we might need to also start to change some ideas of why we access memory, right? And that's something that requires assembly most of the time, or, things. And the other thing is about RISC-V, or, this acceleration extension. Sometimes they're very exotic. And so, for example, I have patches that do not have the guts to send to bNutils mailing list, right? Because, some extensions are just very, very, very exotic. So, I think the hardware side of things is something that, possibly because I'm working on the hardware side of things, I'm more worried about the hardware rather than the high-level software, but that's my bias. And I think this is a big part that wasn't been, I was late, but I think it hasn't been discussed today.
send something, I will happily. If you do want to send something to the binge list, I will happily. I mean, even if you just want comments and not like submitting it as to be added, but just have a look.
Absolutely. I think that's the other project Pietra's working on. She's doing a RISC-V extension for AI.
Well, I just want to say thank you for coming, and please come back next year and tell us what's happened.
Yeah. But yeah, I think that's all for me. Thank you for attending, and thank you for the contributions. Yeah, that's all.